Hello everybody, welcome into another lesson. So today we are going to talk about vectors in space. Now earlier in the course we talked about vectors in the xy plane. Well, it should also be no surprise that we can have them in space when we have x, y, and z coordinates. To find a vector, it's the exact same way as finding a vector in 2D. You have your initial point P to your terminal point Q. To find vector PQ, which is denoted by a half arrow above PQ, you just simply subtract your second x component, subtract your first x component from your second, your first y component from the second y coordinate, and then your first z coordinate from the second z coordinate, and then that is what's called your component form of the vector with these angled brackets. That's how you would write the component form of a vector. Also, another way to write vectors, it's the exact same thing, it's just a different way of writing it. You have what's called the linear combination, where it looks like a sum, but it's really not. It's just going to be, you have the I and j, which denoted your x and y positions, and then in a z variable you have k. So you would have I, j, and k in the three-dimensional plane, or in the three-dimensional space rather, and it's important to specify that I does not equal the square root of -1 for this. This is just simply denoting the x position, the y position, and the z position, or the change in each of those variables for the vector. So let's get started finding a couple of vectors here. So it's going to be actually pretty easy. So let's see, point P is at the order triple 6, 4, -2. Point Q is at the point 1, 1, -3. So we have the initial point, point P, is at 6, 4, -2. I'm going to go ahead and plot that just so I can illustrate what's going on. Alright, so 6, let's see, 1, 2, 3, 4, 5, 6, right about here, 2, 3, 4. So 4 is about here in the y position. And then if I go down 2, that would be roughly 6, 4, -2. Now I need to find point Q. So here's point P. Now point Q I have at 1, 1, -3. So here's about 1 on the x-axis, 1 on the y-axis. Let's go down about 3 units. And there's my point Q. So I've just plotted my 2 points. Now, if you were to illustrate this graphically, you always start with the tail of the arrow at your initial point P, draw to point Q, and put an arrowhead on your terminal point. Point Q is your terminal point, and that is going to denote vector PQ. So what is vector PQ? We'll start in component form. So vector PQ would start as your x2 coordinate of 1 minus your y2 coordinate of 6, your x2 coordinate of 1 minus your x1 coordinate of 6, your y2 coordinate of 1 minus your y1 coordinate of 4, and then your z2 coordinate of -3 minus your z1 coordinate of -2, which would actually turn into -3 plus 2. So to simplify this, vector PQ would end up being -5, -3, -1. That would be vector PQ, which means I'm going backwards 5 in the x direction, backwards 3 in the y direction, and down 1 in the z direction. So that is my total vector PQ, -5, -3, -1. And honestly, this should be ringing a bell from when we did vectors earlier in the course. Wasn't super long ago, but it was about midway through the course. Now we're on the final unit of the course, so I know it's been a while, but alright. Let's do another one. So we have point P is at -7, 3, 5. Point Q is at 0, 0, 2. Alright, so we have point P, the initial point is at -7, 3, 5. Let me go ahead and plot that. So -7 in the x, so let's see, 1, 2, 3, 4, 5, 6, 7, right about here, over 3 in the y direction, right about here, then go up 5 in the z direction. So here's my point P, my initial point, at -7, 3, 5. Now I need to find my terminal point, 0, 0, 2. That's going to be roughly right about there for my point Q. So point P is my initial point Q is my terminal point. So I'm going to take the tail of the arrow at point P, draw it to point Q, and put the head of the arrow at point Q to denote that's where I stopped. So now I have illustrated vector PQ in the graphical sense. So let's go ahead now find that actual vector. So take my x2 of 0 minus my x1 of -7. That would actually turn into 0 plus 7. And then, let's see, I'm going to take my y2 of 0 minus my y1 of 3. And then take my x2 of 2 minus my z2 of 2 minus my z1 of 5, giving me my vector being 7, -3, -3. So the vector in this case would be 7, -3, -3. So finding the vectors themselves are pretty simple. I think we probably have a good grasp on how to actually find a vector. Now, sometimes instead of vector PQ, you may also see it denoted as a vector of one letter. You may also see it denoted commonly as vector V, but really you could assign any letter to vector V. You could say W, U, what have you. Sometimes also in textbooks, largely, you may see it as a bold lowercase v without the arrow. That also denotes a vector. But since I'm not writing in a textbook and I don't want to use that much ink, we'll just use the half arrow notation above a lowercase v. Now, if we recall, let's talk about scalar multiplication. So let's say I have some vector v in component form. I have components v sub 1, v sub 2, v sub 3. That'll be my regular vector v. Well, if we remember about scalar multiplication, I just have some constant c outside the vector. I can distribute that constant through my components. So this would just end up as c times v sub 1, c times v sub 2, and c times v sub 3. Now, here's the thing. If my constant on the vector is positive, that means the vector's moving in the same direction as your original vector. If my constant is negative, that means the vector is moving in the opposite direction as my original vector. So that's something to keep in mind. Negative, opposite, that makes actually a lot of sense. So let's just do a few scalar multiplications. So let's say I have a vector v in component form that is 1, 1, 3. So vector v in component form is 1, 1, 3. Well, if I take 2 times vector v, that means for 1, since this is a positive constant, a positive scalar, that we're going to get a vector moving in the same direction as 1, 1, 3. I'm just going to distribute that 2 through all my components. This would turn into 2, 2, 6. And let's say now I take the negative of v. So I have the negative of v. That means I'm going to get a vector moving in the opposite direction as my original. So this would turn into negative 2, negative, whoops, I don't know why I kept the 2. Excuse me. I need to take that on the original vector. This would turn into negative 1, negative 1, negative 3. That would just give me a vector moving in the opposite direction as my original. And let's say I take 3 halves, because you can also have decimal and fractional scalars. So I just take that 3 halves, multiply it by my vector v. So that's going to be 3 halves, 3 halves, and 9 halves. That would be 3 halves times vector v. And then if I take 0 times vector v, well, that's going to end up then being, of course, 0, 0, 0, which is actually called the zero vector. If you have components that are entirely zeros, that's called the zero vector. Alright, so that's an example in component form. Let's do one in combination form so you can get familiar with that notation. Because in a couple lessons from now, when we talk about the cross product of a vector, it relies solely on linear combination form. So let's say I have vector v is 2i plus 2j minus k. Well, we know this is a linear combination. This, of course, would be the exact same thing as 2, 2, negative 1. That's how the linear combination works. It would be 2, 2, negative 1. Well, we're not going to use the component form this time. We're going to rely solely on the linear combination. So let's take 2 times vector v. Let's distribute that through the linear combination. You would end up getting 4i plus 4j minus 2k. And again, this would be a vector moving in the same direction because it's a positive scalar. Now let's take the negative of v. So if I take the negative, that just means I'm getting a vector moving in the opposite direction. I'll just distribute that my negative through the linear combination. I would get negative 2i minus 2j plus k. That would be the negative of my original. Okay, now let's say I take 5 halves times vector v. So distribute that 5 halves through my linear combination. 5 halves times 2 is 5. So I would get 5i plus 5j minus 5 halves k. That would be my vector in linear combination. Now, if I take 0 times vector v, in linear combination, this would just be 0 to denote the zero vector. I don't have to sit there and write 0i plus 0j minus 0k. I can just write 0. That would denote my zero vector. Now I'm just going to show you something here about, let's say one of these linear combinations is 0. So, or let's say the component form, you have 1, 1, 0. In the 3D plane, of course, this means the z direction is 0. How would you write that in linear combination? Well, you would just write I plus j. You don't have to write 0k. You can just write I plus j. Now let's change this a bit. Let's say I have 1, 0, 1 for vector v. How am I going to write that? Well, I'll have a 1 for my I. I don't have to write plus 0j, but I would just write k. So notice I have an I and a k, I don't have a j. That means my change in y is 0. So if you see some form of I plus k, that means the j is 0. That means your change in y is 0. And then, of course, you guessed it, what we're going to do, we're going to do 0, 1, 1. So let's say I have 0 for my x component. I don't have to write 0i, I can just go right to j plus k. So this would be right to j plus k, I don't have to write 0i. And of course that means I have no change in the x direction, but my y and z components are changing. So that's how you would see the same vector in the linear combination form if you have a 0 entry. So keep that in mind. Alright, so we've talked about vector scalar multiplication. Now we should also talk about vector operations. So let's say we want to take let's do vector u equals -1, 3, 2. Vector v equals -1, -2, -2, and then we have a vector w. Vector w is going to be 5, 0, -5. If we remember from earlier in the course, when you add vectors, you just simply add their components. So let's do a real quick u plus v. Let's say I want to add vectors u plus v. And actually, let me show you what's going on graphically too. So let's say I go from the origin for vector u. I'll just start at the origin at 0, 0. Well, to find the endpoint, my terminal point for vector v, to illustrate this, I'll go 1 in the negative x direction, over 3 in the y, and up 2. So there would be, here's my vector u. Alright, so there's vector u. Now I just want to add v to that. All I have to do are take my components and add them. So I'll take -1, 3, 2 plus that 1, -2, -2. And then when I just add my components, -1 plus 1 is 0. 3 minus 2 is 1. 2 minus 2 is 0. So u plus v should be 0, 1, 0. So how do I add vectors graphically? I started with vector u. If you add a vector to another vector, you start at the head where the arrow is. and you add that vector to it. So I'm going to go 1 in the x direction, 1 in the x direction, left 2 in the y direction, down 2 in the z direction. Alright, let me do this here. Here's vector u. Vector v would be about right there. Draw the arrow there. And then how you get your final result is the sum of vector u plus v is going from the arrowhead of the second vector to the tail of the first vector. That part here would be u plus v. So this denotes a change from my original position. That's what that is, a change from my original position of just 1 in the y direction and 0 in the other directions. That's what that is for my original position. Alright, so that's how you add the vectors. Now, what if we flip this around a bit? What if we do u minus v? In truth, there is no such thing as vector subtraction. There is no real such thing. But let's just dive into general subtraction for a second. Isn't it true that if you subtract two numbers, that's the same as adding the negative of the other number to the first number? So really and truly what this is the same thing as is taking vector u plus the negative of vector v. That's the exact same thing. That's really how you do vector subtraction, is you add the negative of vector v to it. So what we're going to do now is we're going to take our vector u, which we know to be -1, 3, 2, plus that negative of vector v, which is 1, -2, -2. Well, I'll work inside my parentheses. I'll distribute that negative sign, so this would turn into -1, 3, 2, plus, when I distribute that negative sign, would be -1, +2, +2. Now I really have the setup for u minus v, or u plus negative v. So now I'll just add the components, and I'll get -1 minus 1, that's -2. 3 plus 2 is 5, and then 2 plus 2 is 4. So in total, u minus v is going to equal -254. Alright, so having said that, let's get into a little bit more examples here. Let's spice it up a little bit. Let's say I take u minus 2 times v. So I'm going to take u minus 2 times v. Well, this is the exact same thing as taking u plus the negative of 2 times vector v. That's the exact same thing. So let's do just that. Vector u, of course, is -1, 3, 2, plus, inside the parentheses, I'll have -2 times my vector v, which was 1, -2, -2. Now let's distribute that -2 in the parentheses, so I'll have -1, 3, 2, plus distributing that -2 gives me -2, +4, +4. Now all I have to do is add these two vectors. So -1 minus 2 is -3. 3 plus 4 is 7. 2 plus 4 is 6. So I end up getting that u minus 2v is -376. Alright, let's do one more with vector addition. Good one. 7u plus v plus 1/5 of w. So you can add more than two vectors. You can add infinitely many vectors together if you wish to. You're just going to add all of their components together. So notice v is left alone. It maintains a scalar multiple of 1 for the original vector, but you have 7, w you have 1/5. So what we're going to do now, put some parentheses around the 7u. This would be 7 times that vector u of, I should probably make an angle bracket for the vector, -1, 3, 2, plus my vector v, we've already determined to be 1, -2, -2, and then 1/5 of w, so this will be plus 1/5 times that 5, 0, -5. Well, first let's just do all the distributing in our parentheses. So this would turn into, distribute the 7 in the first vector, you would get -7, 21, 14, plus that 1, -2, -2, plus, take that 1/5, distribute it through your third vector, so that'd be plus 1, 0, -1. Now we've simplified all these by distributing our scalars, by multiplying the scalars. Now for each of these three vectors, we'll just add the three components together. So -7 plus 1 is -6, plus 1 is -5. 21 minus 2 is 19, plus 0 is 19. And then 14 minus 2 is 12, minus 1 is 11. So the sum of these vectors added together gives you -5, 19, and 11. Alright, so we got two more topics to talk about today. The magnitude of a vector as well as a unit vector. But first let's talk about the magnitude of a vector. Alright, so the magnitude goes off of the distance formula. So for the magnitude, so let's say you have vector v has just arbitrary components v sub 1, v sub 2, v sub 3. Well, yes, the magnitude goes off of the distance formula because your vector components are definitely the difference of two ordered triples, right? So to find the magnitude of a vector, it looks like a double absolute value symbol with that vector v notation inside of it. All it is the square root of v sub 1 squared plus v sub 2 squared plus v sub 3 squared. That's all the magnitude of a vector is. The magnitude's just a fancier term for length or distance. That's how you word it for when you're dealing with vectors. It's called the magnitude. So it's nicer working with magnitudes because your vector components already denote the distance between your two ordered triples. So all you got to do is put those components in, square them, and take the square root, you have your magnitude. Which means the magnitude's always going to be positive because taking the square root you can't get a negative. So let me find a new marker first. And now Let's do a couple of examples of magnitude. So let's see here. Vector v has component form 7, 8, 7. We want to find the magnitude, or other words, the length, the distance of the vector. So all I have to do is take the square root of this 7 squared plus 8 squared plus 7 squared, which would give me the square root of 49 plus 49 plus 64, which would give me the square root of 162, and I feel like that simplifies some. Sorry, I wanted to get my phone, which is my calculator. I feel like that's going to simplify quite a bit. Yes, it actually turns out to be the square root of 81 times 2, which we know to be 9 times the square root of 2. So the magnitude of this particular vector is going to be 9 times the square root of 2. Now let's do one in component form. Not component form, linear combination form. So let's say we have 4i minus 3j plus 7k. So this time they give us the vector in linear combination form. Really no different, it's just how it's expressed. I want to find the magnitude of that vector, so all I need to do are take my coefficients on the I, j, and k and square them underneath the square root and add them together. So I'll take that 4 squared plus that negative 3 squared plus that 7 squared. So let's square every term under here. 4 squared is 16 plus a 9 plus 49. So that's going to give me the square root of, let's see, 25 plus 49. That's going to be the square root of 74. And that's really the best I could get. It's not going to reduce anymore. So the magnitude of this vector is the square root of 74 units, which is more than 8. It's over 8. Alright, so that's finding the magnitude. Now finding the magnitude of a vector actually has a good use, which is going to come up quite a bit. It's been a while since you've heard this term probably. It's called the unit vector. So the unit vector. So often it's useful to find what's called a unit vector. A unit vector is a vector in the same direction as the original vector you're given. The only difference is the magnitude will always be 1 for a unit vector. So it's often asked you to find, they will often ask you to find a vector in the same direction as vector v. They may also ask you to find one in the opposite direction as vector v. In the same direction as vector v is going to be a positive scalar on vector v. In the opposite direction, it would be a negative scalar to denote the opposite direction. So, how do you find a unit vector? The formula for a unit vector, so if we have a vector v, we often denote the unit vector as u. It doesn't always mean that u is a unit vector, but if you're relating it to the original vector being the unit vector, What that is 1 divided by the magnitude of vector v times vector v itself. That'll end up giving you the unit vector. So you take 1 divided by the magnitude of vector v, you'll get the resulting scalar, multiply it by vector v, and then you'll have your unit vector. And by default, that is always going to be in the same direction as vector v. If you wanted to find one in the opposite direction, all you have to do is take this 1 over magnitude of v, slap a negative sign on it, and you just now found a vector in the opposite direction. So let's work on some examples here. In this case, they give you that, let's see, vector v is equal to (5i) minus 12k. So we got 5i minus 12k. Notice there's no j term. Well, really that means there's a 0 on my j, which means there's 0 change in the y direction. But that's okay. We want to find a unit vector in the same direction as v. So also, why don't we tack on find a vector in the opposite direction as v. Alright, so let's start in the same direction. In the same direction, I need to find first the magnitude of vector v. Actually, before we even do that, why don't we start finding the magnitude of vector v? So the magnitude of vector v, that's going to be the square root of 5 squared plus 0 squared plus negative 12 squared, which would turn into the square root of 25 plus 144, which we know to be the square root of 169, which is exactly 13. The magnitude of vector v is exactly 13. Let me put that magnitude symbol here for vector v. So now if we're going to go in the same direction, we're going to say vector u equals 1 divided by that magnitude of 13 times my 5i minus 12k, which all I have to do is distribute that 1/13. I'll end up getting 5/13 I minus 12/13 k. So that would be my unit vector in the same direction as vector v. I would get 5/13 I minus 12/13 k. And then if we took the magnitude of this unit vector, it would in fact be 1. That's how you'll know you got the right answer. Now let's say I wanted to go in the opposite direction. So in the opposite direction, all I have to do is put a negative sign on my scalar multiple I get here after finding the magnitude. And this would just turn into negative 5/13 I plus 12/13 k. You'll just get the opposite result. That's the unit vector in the opposite direction. That's going to be in the opposite direction as vector v. So really pretty simple. Let's do one more. Alright. Vector v equals 8i minus 3j. Sorry, 8i plus 3j minus k. Alright. Vector v, again, a linear combination, 8i plus 3j minus k. So we want to first find a vector in the same direction as vector v, meaning a unit vector, and then we want to find a vector in the opposite direction as vector v. Well, that means we're going to take the negative of that unit vector. That's all that means. So if we want to, first thing we want to do is find the magnitude of that vector v. So that would be equal to the square root of that 8 squared plus that 3 squared plus that negative 1 squared, which is going to then equal the square root of 64 plus 9 plus 1, which is going to give me the square root of 74. So my magnitude of vector v is the square root of 74. So to find the same direction, my unit vector, vector u, is going to equal 1 over the square root of 74. So 1 divided by my magnitude times my vector v, which would be that 8i plus 3j minus k, and that would end up giving me 8 over the square root of 74i plus 3 over the square root of 74j minus 1 over the square root of 74k. And then if we want to find in the opposite direction, all I'm going to do is negate this. If I negate my unit vector, I'll end up getting negative 8 over the square root of 74i minus 3 over the square root of 74j plus 1 over the square root of 74k. But in either case, you take the magnitude of either of these unit vectors, you'll end up getting 1. You would get exactly 1. That's what's true for a unit vector. Alright, so I think that's it for this lesson. Next lesson we're going to talk about the dot product of two vectors, which will be more of a review. We'll talk about finding the angle between two vectors using the dot product. We'll even talk about, what else? Orthogonal, parallel vectors, and we'll also talk about testing for collinear points. So I hope everybody has a great day. Take care.